we're going to talk about linear temporal logic and linear dynamic logic on finite traces. Let me see if I can. Okay, I can move around. Yes. So first of all, the motivation. The motivation is I am personally working on AI agents, and somehow linear temporal logic on finite traces are really a fantastic tool from the computational point of view to handle this kind of agent, essentially because they give a lot of concreteness to this logic automata gains triangle that is typical of formal methods. In particular, you start with this finite trace variant of linear temporal logic. The correspondent automata are DFAs, which are very nice to handle. And then over these DFAs, you play reachability games, essentially. And then these reachability games will give you strategies, essentially, to fulfill the LTLF specification. So this triangle allows you to do decision making for LTLF arbitrary specifications. So planning, you can think about planning in AI through using essentially DFA technology, which is actually very effective. So we are working with linear temporal logic. Obviously, you know, there is two big families of temporal logic, the linear time and the branching time. And so in linear time, we see the time as lines, okay, sequences of instances. In each instance, you have proposition evaluations, essentially. In branching time, you have trees. And in these trees, what you have somehow that if you get to a node of this tree, behind you, there is a history that leads you to that particular state. And in front of you are the choices. And this idea of having the choices, I mean, it may look at first sight pretty interesting because you say, oh, okay, I want to have free will, I want to have choices in front of me. But the problem is in front of who? Because who is deciding on these choices that you have? And in fact, if you have a closed system, it's the system. But if you have an open system in which the system is immersed in an environment, you really don't know who's choosing, who's making this choice. Actually, it's a sort of cooperative choice. And so this additional power the branching time gives you is not very useful. Okay, it's not very useful. So since we are really focusing on decision making, planning decision making, we actually are pretty satisfied in working with linear time instead of branching time, and do synthesis instead of doing model checking over this logic. So the idea of the use of temporal logic on finite traces in AI has been present since a long time. So in fact, if you scan the early papers, these are papers from the end of the 80s, beginning of the end of the 90s, 2000, you see that a lot of these papers are really talking about LTL, but in a finite trace variant, okay? And this interest on finite trace is actually due for a very precise reason somehow. And it is that in AI, we really are thinking about an autonomous agent that plans its action. So you give a goal to the autonomous agent, and the agent will actually synthesize a plan, a strategy, a policy, okay? It takes into account also the environment and allows to act to satisfy the goal. The point is that we are in a sort of cycle in which we get the goal, we think about how to solve it, we execute the plan, and then we get another goal. So we are in a sort of loop in which we continuously get goals and continuously generate plans to solve these goals. But notice that for this loop to have sense, it is somehow crucial that you don't spend all your life executing the plan. Because if you spend all your lives executing the plan, you need to be intelligent only once. But then the intelligence should remain in the designer mind, should not be externalized to the agent mind. Okay, so in the end, said, no, it's the agent that thinks, it's the agent that does the synthesis, and the agent does these things many times in his life, and so it becomes very natural that somehow this task, after a while, end and stop. And so this is why finite traces is so important in NI. There is another area in which finite traces are also very important, and is business process management. Particularly in business process management, they talk about processes, okay? And these processes and instances are all somehow guaranteed to terminate. So they start at a certain point and then will terminate by a certain, after a certain number of steps. So they are always being focusing on finite traces as well. And in particular, at a certain point in 2006, they were looking at processes that were very complex, very full of exceptions. And they started thinking that maybe they should not describe this process as some sort of programs, high-level program, but they should describe them as constraints, particular constraints in LTL. And then if you have constraints in LTL, then you want to essentially generate a control flow out of the constraint, the QL. But then the question arises, but what about the entire space that these rules are generating? Is the entire space itself a process? And the answer is that if LTL is interpreted over finite traces, it is. The entire space of choices, it is itself a process. And this has been a very interesting result from them. And since then, there is an entire branch of business process management that looks at declarative process specification, essentially written in LTL on finite traces. So what is LTL for finite traces? Is LTL, essentially exactly the same syntax, except that you have a problem that you are interpreting things on finite traces, and so you don't have the fact that there exists always a next instance. Okay, the trivial part that there is always a next instance fails, because at the last moment you will not exist a next instance, and this actually gives rise to two forms of next. A strong next, which is the usual next we use in temporal logic, that says there exists an instance, and in that instance phi is true. And a weak next, here denoted with a black circle, that says that if there exists an instant, at that instance phi holds. Okay? And one is the negation of the other, and we don't have the famous equivalence, the famous equivalent we have in LTL of infinite traces, in which we have the next phi is equivalent to not next not phi. This is false here, because what is true is that we next phi is equivalent to not next not phi. Also, we have a way of denoting the last instance of the trace. And so now on the trace, we have two reference points, not only the beginning of the trace, but also the end of the trace. We can talk about these 2 points. And obviously, you can use, instead of symbols, by now we know that this logic is very nicely interpreted in English itself. So you could use even directly English terms like eventually for sooner or later, always to say that something goes forever. Here, forever means until the end of the trace, and until that says something pi 2 will eventually happen, and before that, pi 1 or it's always 2. By the way, until it's a little bit of a false friend with respect to English, and this leads to a lot of misconception in writing logic in a naively way. But if you get if you start understanding the meaning of the various operator from a mathematical point of view, then you become pretty good at writing these specifications. So let me give you some differences between the LTLF, some example difference between the LTLF on infinite traces and finite traces. On infinite traces, for example, eventually A means sooner or later A happens. And on finite traces, it means exactly the same thing, except that this sooner or later must happen before the end of the trace. Okay, before or at the end of the trace. Always A on infinite traces means A all along the entire trace, and also on finite traces it means exactly the same thing. It goes along all the trace until it ends. And then if you have, for example, eventually next A, okay, so this means that sooner or later A happens, and since you want to have at least one other step, this will happen before the last time. However, things become a little bit more difficult if you start considering the fact that next implies the existence of the next instant. So you have to be very careful if you want to state the existence of the next instant or not. For example, if you say always next day, on infinite cases it means except for the first instant, A is going to be true forever. Okay? But on finite cases, it means false. Okay? Because you cannot have that in every point of the trace there exists a next instance, since at the last moment there will not exist. Okay, cannot exist a next instance. So one has to be very careful in choosing the right next. So to understand, always ask yourself, but do I want to assert the existence of the next instance, or I just want that if the next instant exists, something is true on it. Okay, and so while in infinite cases you wouldn't care about this aspect, here you really care about this aspect. For example, if you want to say always next day, in finite traces, you should use with next. It's also possible to express in this logic pretty sophisticated thing. Here there is, for example, a coding of strict planning domain into LTLF and the reduction of plan existence to plan satisfiability of a certain formula in LTLF. And I mean, I don't know how much you know about AI, but there is another very famous way of describing action in AI that is called successor state axiom in situation calculus, and you can easily capture those in this logic. Expressive power. So what is the expressive power of LTLF? Essentially, LTLF has the expressive power of first order logic over finite sequences, in which you have unary predicates and one binary predicate that is the successor. Okay? And it's very easy to take an LTL formula and to translate it into first order logic. It's linear. Here is the translation. And we know that also the vice versa is true. Okay, this is a classical result of specificity of ATL and LTL. However, can we do better than that? So what about monadic second order logic? Can we use monadic second order logic? Okay, and we know that monadic second order logic is actually correspond to regular expression if you interpret them over finite traces. So regular expression are pretty much used. So you may ask yourself, should I use regular expression instead of LTLF to describe as my logic? And however, the problem of regular expression is the regular expression are not close under the Booleans. In the sense, obviously, yes, from the expressive point of view, they are close, but the negation of a regular expression is something very complex to compute. You actually have to compute for the regular expression, the automaton, determinize it, and then complement it, and then re-extract the regular expression. So this is really a mess. And it means that as a logic, regular expression don't work very well. Unless we start adding to regular expression complementation, etc. But if we do that, then regular expression become really untrackable because essentially they become non-elementary. So the regular expression enhanced with what you need to make it a logic are a little bit strange piece. On the other hand, maybe I don't have to say to you, but on the other hand, first of the logic on regular on finite sequences correspond to star pre-regular expression. This is a proper subset of regular expression, where essentially we give up the fixed point computation of star in favor of a very simple form of star that means always essentially. So on the one hand, we have this LTLF. On the other hand, we have these regular expressions. Can we have a good logic, a nice logic for monadic second order? That is the specific power of monadic second order logic. And the answer is, in fact, we can. And we can look at the logic that was created in the 70s to talk about program schemas, okay, while, if, etc., over, we say schemas because essentially it's a propositional logic. So it doesn't really look into the real test and the real first order element that you might have in a test. Okay, and so this is called propositional dynamic logic. Propositional dynamic logic is normally interpreted over trees. But here instead, we're going to use the syntax of propositional dynamic logic by interpreting it over traces, over finite traces in particular. And what you have essentially, instead of having eventually, you have a enhanced form of eventually, in which you don't only say that eventually you reach a certain instant where phi, certain point position where phi is 2. But you say that in order to get there, okay, you're going to satisfy a regular expression, okay, sometimes called the program, okay? And you have also the dual, and the dual says that every position that is reached through that regular expression is such that phi holds, okay? This is the dynamic, the linear dynamic logic. And what we have for the linear dynamic logic is that actually we can capture very easily linear dynamic logic the linear temporal logic, and also we can capture very easily regular expression with linear dynamic logic. So we have exactly the same expressive power as monadic second order logic, but we are close and hands or without any real difficulty. By the way, notice that this idea of extending LTL with regular expression actually comes from far, and it is even included in standard formalism like Forsbeck and PSL. Okay, so maybe I'm going to skip this because I don't think that. And so just let me give you some example. For example, it's very easy to write things like every time that person P requests for coffee, eventually gets coffee. Okay, so in this logic, you would say it is always the case, true star. Okay, so every position you reach by executing true arbitrarily many times. If there you find that request P is true, then there exists a sequence, okay? There exists a position that is reachable for a sequence of true finite, okay, where the coffee is served. And similarly, you can say a lot of properties. There are also properties that are really very strange to say in linear temporal logic that are easy to express in dynamic logic. For example, look at this. Okay, it is always the case that if now is at, then if the air conditioning is not on, then you turn on the air conditioning. Otherwise, the air conditioning is kept off. Okay, so you see that now we are mixing a procedural aspect. You see the regular expression. Okay, now with this simplification, with this abbreviation of if, then, else, and while. Okay, here there is also if, then, else. We are using really regular expression to express some sort of procedural element in the execution. And this is very nice. Actually, it's very nice, and it was observed in AI that this kind of procedural knowledge is actually very useful to constrain how the agent behaves over time. So, for example, there was a language called Golog that was all about constraining the agent through this programming language that, however, was completely interpreted in logic. It was a sequence of calculus formula in the end. Okay, so now let me go to automata. So what is the point of this logic? The point of this logic, the key point is really this one. And if you have an HTLF formula or an LDLF formula, they are exactly the same. Okay, a trace satisfies the formula if and only if the trace belongs to the language of a regular automaton. Okay, and which regular automaton? Actually, it's very easy to write an alternating finite state automaton corresponding to the formula. You essentially use the semantics we're going to see in a moment. Okay, actually, linear, you can create this in linear time. Okay, both for LTL and NDLF, LTLF and NDLF. And then if you want a non-deterministic automaton, you can non-determinize an alternating automaton, paying an exponential time cost. And if you want to have a DFA, you can have a DFA as well, paying a second exponential time blow-up. It has to be said that these exponential blow-up are really worst case analysis. And in many cases, it is not the case that you have this blow-up. So first of all, we know that it's very often the case that going from NFA to DFA does not increase exponentially the size of the automaton. Okay, this is a very well-known fact. It happens actually in very many cases, including the fact that you are using grep or in Unix, which works with regular expressions, but we know that in order to actually compute the code corresponding to the regular expression, you have to get a deterministic automaton. And so you would spend an exponential, the deterministic automaton should be exponentially larger than your specification, but in fact it's not. And this is the reason why you use grep every day in Unix. More generally, many formulas of interest are really create automata that does more. So let me talk a little bit about this alternative automata. I don't want to go through the alternative automata. I just want to give you this single slide, okay? And I wonder if I have exactly. This is the slide that I want. So actually, to create the alternating automaton, what you will do is to use the semantics of the formula. So the first thing is this alternating automaton as alphabet the propositional interpretation that you use in the trace, as states it has the sub-formula of the LTLF formula. And here we have to be careful because the sub-formula of any fixed point based logic are not the syntactic sub-formulas, but are the sub-formulas of the corresponding fixed point equation. Okay, and I'm going to go to it in a moment. And this is why we say Fisher-Lerner closure. And then you have as initial state the formula itself. As final state, and nothing is final. You will simply consume the formula while executing. And the transition function is written all here. Okay, so it's very, very small. And look what it does. Okay, so let me see certain cases. For example, next phi, what it says that independently of what you read now, next your state will be phi, unless you are at the last moment of the trace, in which case it's going to be false. Okay, you fail. And for eventually, let me look at eventually. Eventually is very interesting. So in order to understand eventually, we have to go to the fixed point equation of eventually. Fixed point of equation of eventually says the following. Eventually phi is equivalent to check that phi is true now, or next, strong next, eventually phi holds. Okay, so notice this is a fixed point equation because if you replace this with z here and there, you have a fixed point equation, and now you look for the smallest solution of this, and this will actually give you the meaning of eventually phi. And now if you go to the alternating automata, you see that the alternating automata is really decomposing eventually phi using the fixed point equation, and says the transition for eventually phi reading the current symbol, the current interpretation, is the transition that you will get but recursively by looking at the state phi, or the transition that you get at looking at the state next eventually phi. Okay, so you see, you are recurring using this structure of the fixed point equation. Now, once you have this alternating automaton, with standard technique, you can transform it into a non-deterministic automaton. And as I told you, for many formulas, it's actually very easy to get the corresponding automata. There are tools available to actually construct the formula. Interestingly, these tools don't really use, most of the best tools don't really use the actual optimal from the point of view of complexity technique, but they often just translate the formula into first order logic, and then use Mona to get Mona. It's a tool for transforming first order logic on finite traces to the it does many things, by including transforming first order logic on finite traces to DFAs. In spite, this step is non-elementary. So instead, you go from a double Einstein to a possibly non-elementary technique. And actually, it has been shown pragmatically that you can get better result from this non-optimal translation than from the optimal translation. And the very best tools that are around, the one that won the competition this year, they are all based on taking the formula, decompose it, and then take the single pieces of the formula and translate it through Mona, or something equivalent to Mona, something non-elementary, to a DFA, and then compose the DFA. So it's pretty interesting that the best tools are not following the computationally, the optimal procedure from the point of view of computational complexity. By the way, this happens many times. I also want to mention that there is a relationship with pure past LTL. So what is pure past LTL? This is an LTL that looks at the trace backward, okay? And now notice, when you look at the trace backward, the trace is always finite, right? Because you are now in a certain instant of time, and you look backward, okay? And by looking backward, you are looking at the position from now to the starting position 0. They are finite remaining. It's a finite trace. It's a finite trace formalism. Okay, so pure path LTL, it's a finite trace formalism. Okay, and in fact, it's actually equivalent to LTLM. You can show that these two have both the expressive power of the logic, so actually they have the same expressive power. The difference is, however, that in pure past LTL, you are looking at the trace backward. In LTLM, you are looking at the trace forward, okay, going in this direction. Translation to first order logic is actually very, very nice to see this translation, because this translation, you see that it's identical except for this point over here, okay, this point over here, where you are using the quantified variable in the previous position or in the next position. Okay, this is very nice. Okay, and then the same idea applies for since that is the equivalent of until. It's also interesting to so they have the same expressive power. So you might ask yourself, okay, but how is it to translate one into the other? Okay, unfortunately, the answer it is very difficult. First of all, both of these logic are exponentially more succinct than each other. Okay, so there is a formula in pure path LTL that is provable exponentially smaller than the corresponding formula in LTL, and vice versa. And vice versa. The best techniques that are available are 3x time. Okay, and you, for example, there is a discussion in this survey that we published in, I think, July 2020. And essentially, no one really looked into good way of doing this translation yet. Okay, and systematic translation exists for certain fragments. Okay, and also for many formulas that are of common use. For example, the catalog of the declare formula or this PDDL3 formula that are formula used in planning. Actually, most of these formula can be translated from pure past to LTLM in polynomial time. Okay, but in general, we have no really good way to move from one to the other. There is a very important observation to do on pure past LTL. So you can put any pure past LTL formula in something that we can call previous normal form, essentially exploiting the fixed point equations. Okay, notice the fixed point equation for eventual in the past, for example. It says phi is eventually true in the past, okay, if phi is true now or previously, in the previous step, it was true that eventually phi in the past. So what it means that I can take any formula and put it in a normal form in which, okay, I only talk about what is true now and what is true at the earlier step, okay? And again, here I need to use both positive, both strong and weak next in general, okay? Now we have the same thing also for LTL. We can also put it in a special normal form using the fixed point equation so that the formula looks at only the current instant and the next instant. The problem of the next instance is that you don't know the next instance, but the previous instance is written in the trace. So when you use these fixed point equations, there is a big advantage to be gained in the sense that the past is known because the trace, in any case, unfolds from the beginning toward the end. Now, this observation, so the fact that while if you're using LTLF and you use this the composition, what is true now, what is true next, you have to guess what is true next because what is true next is not written in the trace. When you do this for the past, you don't have to guess anything. Everything is written in the trace. And this actually gives an exponential advantage in obtaining the automaton corresponding to pure past LTL. You can obtain a DFA of pure past LTL in single X time instead of double X time. Okay? And the reason, actually, I mean, there is a language theoretic reason, but there is a very nice way of seeing this. I can show you here in this single slide a symbolic version of an automaton, a factorized version of the DFA that is obtained in a linear time with respect to the formula. So obviously it's a factorized version. So when you expand it, you're going to have an exponential space of states. Okay, but if you consider it factorized in components, you can have it in a very, very compact stage. Okay, so let me tell you a moment what this is about. So you have the automata, you have as language the set of oppositional variable. As state, you have all the formulas, okay, of the form, okay, previously phi 1, okay, that you find in the subformula, in the syntactic closure of the original formula. Assume that the original formula is only previously, it's obtained compactly by using only previously and seeds. Okay, so that we have the minimum number of operators. Okay, so the previously, you can take all the formulas of the form previously. So if we go back here, when we do this, we don't have anything in weak form. We have only things on strong form. Okay, so we can keep track of the value of this proposition starting from the beginning in the state of the automaton. And then you have a flag to tell you if a certain formula is true. I'm actually missing a slide here. Okay, sorry, I'm missing a slide. I don't know why, but okay. Anyway, it's not important. So now what I can do, I can compute how I transit from one state to the next, okay, by composing the transition of each, how to update the value of each of these formula. So I have a way of updating the value of each of this formula reading the current instant and considering the previous value. And I can use that to actually create the transitions for the entire state. So the result of this is that I have a factorized symbolic version of the automaton in polynomial time with respect to the formula, which is really very interesting. Now, let me tell you that this pure past LTL has been used in the past, especially for characterizing expressivity of fragments of LTL on infinite traces. Okay, in particular, we have this safety progress hierarchy, okay, by Knueli and Mann, Knueli later, that actually divided all the formulas of LTLF into safety formula, guarantee formula, obligation formula, recurrence formula, persistent formula, etc., etc. And they have a syntactic form, you can see it over here. And for example, for safety, they are formulas of the form always in the future, and then what? We have a formula in pure past LTL. Okay, they are all of this shape. Okay, guarantees, okay, of co-safety. So what it means, eventually in the future, you reach a state, okay, a position such that the trace generated so far satisfies B, where B is a pure path level formula. And also for recurrence, if the many often you satisfy a certain pure path LTL formula, or except for a beginning in which you do, except for finally many times, a certain formula is always satisfied, and so on and so forth. Okay. Now, what is super interesting, if you look at this safety progression classification, they are really classification based on talking about infinite trace property through finite trace property. So when you talk about safety, for example, what you really are saying, you are saying safety is an infinite trace property, okay? And what it says that all the empty prefixes, all the non-empty prefixes of the traces that satisfy the property, in fact satisfy a finite trace property. And also guarantee there exists a prefix of an infinite trace satisfying the infinite property that satisfies a finite state property. So it is all based on the essentially the structural property is coming from a finite state description, while the behavior ad infinitum comes from the infinite trace property. But the behavior ad infinitum is very limited. There are only safety property, guarantee property, obligation property, recurrence property, persistent property, reactive property. So what we say ad infinitum is somehow not that much with respect to what we say at the on the finite trace. Okay, although we require what we say on the finite trace to happen in the off and etc. By the way, this is general. This is true in general. If we get straight to first order logic, then we have LTL safety property, LTL guarantee properties, etc., etc. And then also syntactic guarantees. Okay. And so here there is an interesting observation to do. Actually, you use LTLF to characterize safety property, to characterize guarantee property, to characterize obligation property, recurrence property, persistent property, reactivity property. And the fact that you say you can use LTLF, now you start thinking, but it doesn't mean that I can use a DFA-based technology to talk about this kind of properties. And while we know that this is true for safety, it's true for guarantees, it's true for obligations, okay, you can use essentially arenas or automata that are built on finite, on the phase, although then the acceptance condition will be much more complicated, maybe a parity condition. But the idea would be, can I use this finite trace characterization to actually generate the DFA out of it and use some composition of DFAs in order to reason with this logic? And the answer, at least for a certain, I mean, in principle, yes. And then in a very effective way, yes, for some of these classes. Now, let me, so I think I have another, I've still some minutes. I want to talk a little bit about reasoning. So first of all, satisfiability. How you do satisfiability in LTLF? Well, you take the formula, okay, you translate it in a time into an alternative automata, you get the non-deterministic automata out of it, and now you check non-emptiness for the non-deterministic automata. And now notice this is an n-log space problem. Also, the transformation of alternative automata to NFA can be done on the fly. So this exponential is eaten somehow by this n-log space, and indeed we get a p-space complete procedure, okay? Which, by the way, is not very different from what happens in the infinite case. Okay, you're not really gaining anything. I mean, not much, yeah. And also you can do validity and logical implication with the usual transformation of these services into satisfiability. Also, model checking, you can do model checking by considering essentially the transition system correspond to an automaton. We can take the Cartesian product of that automaton with the automaton of the formula and then do the non-emptiness check also there. Okay. It's interesting, however, to understand what can LTLF say from the point of view of model checking. And essentially, LTLF can only talk about safety property because they are property that need to hold for all the finite trace over the transition system. And so things that hold on all the finite trace over the transition system means that they hold for all the prefixes of all the traces, and this means that it's a safety property. However, there is also some interesting observation that actually a recent paper by Summa Balzal and other that shows that on the other end there is a secondary model checking property. And the secondary model checking property is to check that over all infinite traces there exists a finite prefix that satisfies an LTLF formula. And this problem here, okay, which is not the classical model checking property, somehow a problem that arises, for example, if you want to check a certain transducer, okay, induces some nice property over formulas. This is a free space complete problem. An X-space complete problem instead of a free space complete problem. Okay, now I want to get to synthesis. Okay, and here we have synthesis in a closed loop where everything is under control of the synthesizer. Okay, and this is the case of interest for BPM. Essentially, they want to look at this wide region here, and they want to have these are it's expressed all in a LTL with LTLF constraints. You want to have a control flow, but not that is included in the white area, but that actually capture the entire white area. And this can be done simply by taking the formula and transform it into a DFA, because we have to remember that DFA is a file state sheet, so it's something it's a program. So that's is what we really want when we say a control flow that corresponds to the entire white area. And now let me finish with synthesis. Okay, so all the work on LTLF has been motivated strongly by synthesis, from decision-making synthesis. Okay, and what is the idea of synthesis? The idea of synthesis is we give a specification in temporal logic, in some high-level language, okay, that is understandable by human, for example, logic, okay, and then out of it, automatically, we get a program that is guaranteed to satisfy the specification. And in particular, the kind of specification, the kind of synthesis, the kind of problem we are interested in are the so-called reactive programs. Okay, and what it means reactive program? It means that the input is not given all at the beginning, and we are computing the output at the end of the execution of the program, but the input of the program is given while executing the program itself. So step by step. And so this is of interest every time that you have some sort of interactive computation, maybe a web page in which you are executing parallel with a human that is clicking in order to decide where the program should go. Now, reactive synthesis is a very nice and elegant comprehensive theory. And here there are a couple of surveys that talk about it. And it's also related very much in AI to planning in non-deterministic domains. Okay? And essentially, you can have a game view of this synthesis. So you are an agent, okay? and you are immersed in an environment. The environment is giving you some inputs, and you are giving output to this environment. And this is a loop that is going to repeat arbitrarily many times. Okay, and so essentially you can really see it as a game between the environment and the agent. The environment makes its move, the agent makes its moves, and so on and so forth. Every time we have a round of this game. Okay, and what we want to synthesize the strategy for the agent. Okay, so what we want to synthesize a function that reads the history. Okay, what has happened. In fact, it only need to be the input coming from the environment, and it returns what the agent does. Okay, what are the actions that the agent does? Okay, and notice that when I write something like this, I'm really talking about an arbitrary form of a strategy that essentially is any sort of process with the only constraint that you can use as input only the past and not the future, which is a requirement for our processes. Okay, so now we can say that so we have this game view, and we have an LTLF or an LTLF specification, and we actually partition the proposition in the formula into what is controllable by the agent, what is controllable by the environment. And then what we want to find a strategy for the agent to choose the value of its y, so that together with whatever value of the x, you get a trace that satisfies the formula. This is what we want. So, and how you do this in LTLF, this is very nice. So you take the formula, transform it into alternative automaton linear time, in a deterministic automaton, in a non-deterministic automaton, and in a deterministic automaton. Now you consider this deterministic automaton as an arena. Okay, an arena in which on the edge of the automaton, remember there are the x's controlled by the environment and the y's. No, there are the propositions, but some of them are controlled by you, and some of them are controlled by the environment. And your problem is in this arena, you want to find a strategy to win the game of reaching the final state in spite what the environment does. So these DFA games are really essentially a DFA in which you are partitioning the proposition into what you control and what you don't control. And then when you do the computation in order to win reachability, you use a pre-image for the computation and then a fixed point computation. But the key point is the pre-image in which you choose what the y's, such that they must work for whatever choice of the environment, okay, creating a transition over the DFA game that leads you to the desired set of states. And then you start with the desired set of state being the accepting state, and then you build through a fixed point computation, or least fixed point computation, you build the winning region of this game, and then you can actually compute the strategy by considering how you go from a stage I plus one to stage I of the fixed point computation every time, and this actually gives you the strategy. Okay, here is a little example. This has to be compared to what happens with LTL with LTL synthesis. Okay, so we know that LTL model checking works fantastically well, but synthesis doesn't work that well. And why? There is a very precise reason, and the precise reason is that in order to work with synthesis, you need to have a deterministic automata. You cannot have a non-deterministic automata, because the problem is that the non-determinism helps, okay, the satisfaction of the formula. But in this case, there are two players And so if you help one, you are damaging the other. And so you cannot assign this power of determinism to either of the two, and you need to get rid of this non-determinism. And by unfortunately getting rid of non-determinism for looking on deterministic automata is a really complex thing. And this essentially has ramification in LTLF synthesis. And essentially, while we have that model checking scales up very well to huge number of states from huge number, huge specification, this is not the case for synthesis on infinite traces. But instead, it scales much, much better if you're looking at LTLF synthesis of finite traces. Okay, conclusion. So we start from a formula in this language specifying essentially finite traces, okay, good finite traces, and this can be transformed into a DFA. And once you have DFA, you can do synthesis, as we have done here. You can do many other things. You can do planning. You can mix it. You can combine it with MTPs and probabilistic domains. You can do reinforcement learning. And the fact that you can obtain a DFA instead of a more complex automata is really giving you an edge from the computational point. And I'm finished with this. Thank you very much.